Okay, let's get started. Good morning, everyone. Today we are very honored to invite our seminar speaker, Chiwoo Park, to give us a talk on modeling and analysis of long-shape sequences, application to motion and time study in OR. So here's a brief introduction to Professor Chiwoo Park. He's a professor in Department of Industrial and Systems Engineering in University of Washington. He earned his bachelor's degree in industrial engineering from Seoul National University and his Ph.D. in industrial engineering from Texas A&M. Before joining University of Washington in 2024, he was a professor at Florida State University. Professor Park's research focuses on machine learning and data science, particularly their application in advanced manufacturing and physical science. He is known for his work on shape data analysis, surrogate modeling, experimental design, and the development of digital twins for cyber physical systems. His contribution to the field have earned him several honors, including Ralph E. Paul Jr. Faculty Award in the Brain Pool Fellowship. Now, without further ado, let's welcome our seminar speaker to start his talk. Yeah. Yeah, please go ahead.
Thank you very much, Andy, and then so for the nice introduction. So it's my pleasure to talking in this seminar and about my research. And my background is more like in the applied statistics, but I'm doing some large of the application in the quality engineering and the advanced manufacturing. So today I'm going to talking about one of my is a pretty new research in the using some shape data analysis to understanding some human performance behaviors in the operation research. So just the topics of the today first, okay? And so what I'm interested in to deliver today is we are to understanding some a variation in the shape sequences. So then what I mean by the shape sequence you have some time series observations at each time t, and each time t you have some kind of observing some shape of some d-dimensional objects. And so you have a bunch of this kind of time series data, which is the time series of the shapes. And so main objective here is we like to learn and model the statistical variation in the shape sequences. That is so what I'm interested in to deliver today. So there are some of the motivating example, and we actually working on in the first example in the product shape qualities. And you are producing something, right, in the factories, and then 3D printers, and then so process actually in the changing the form factor of the products. Then is so doing the processing, and then you have some shapes are observed. So each step by step of your processing, and you have observing some sequence of the shapes of your products. And then given the some kind of in the time series data is the forming from the process, and from the beginning of the process to the end of process, you are getting some a time series data of the shapes. Based on that, we try to understand what is the variations of the process in terms of variation in the shapes over the times, and then given that is how we improve the process. That's the one examples I'm looking at. So another is this one is the very old studies we are working on, and then so we are sometimes producing the products. Okay. Yeah. In the previous, right? Okay. So then here is you have a shape sequence, but you have a multiple shape sequence, right? And then so I is going to be as one observation, right? Index for the observation, right? So then each observation you have one entire sequence of the shapes, right? So then you have a bunch of the observation. So then index I is the representing index of each observation. Yeah. So then going back to the another examples, and then so you are producing some products, but you can think of some batch productions, okay, instead of just the one single production like in the additive manufacturing. So this is the one example in the nano manufacturing is that you are producing and synthesizing the nanoparticles. But that's the chemical process basically, and then basically you are producing nanoparticle in the so many number of the particles from the same process, because in the chemical process naturally is in the chemical reactor you are having so many number of particles. So then the output of the process is that you have some bunch of the objects. Each object have the shapes. Then is your quality characteristic for that case is like a distribution of the shapes. And you like to control that distribution of the shapes. Then for doing so, and then you just kind of the monitoring so how the shape distributions are changing over the time. And then through that is that you like to improve process qualities, and based on that. So that's another example. But for these cases, is the sequence is not just the sequence of the individual shapes, and then your observation is the sequence of the shape distributions. Then it's how you modeling that, and how you control that. Yeah. So that's basically another examples. So last example I like to show that is the main focus of the today, and basically we are using that analysis of the shape sequence for the human performance analysis. So basically the human performance analysis is you are kind of doing observation of the human works in the factories, in the healthcare facilities, in some other situations, right? So basically the human performance is the kind of model as the sequence of the shapes, because so your motions are actually described as the human body shapes, and then how that is changing over the time. That is describing the motion of the workers in the situations. Okay, so then basically your human motions from the situation is the sequence of the human body shapes. Then we kind of trying to understanding. So what's the variation over there, and then what is the implication of that variation in the performance in the human. In the operation research. That's actually another aspects of the motivating examples. So then we have a lot of the interesting examples in the multiple different contexts in the applications. So then we just deep into the topics and what's the challenge over there. So then certainly is we are dealing with some sequence of the shapes, right? And then is the first topic we need to dealing with in how we represent the shapes, and that's basically the important topics to first dealing with, and then after that we can move on to the more complicated thing. Then is how we model the sequence of the shapes, right? But the first thing we need to deal with in how we modeling the shape itself, right? So then the shape is a very complicated quantities. It's not numerical data is you are dealing with in the normal time series data. So shape is a geometrical features of the objects, and so that the geometrical feature is how you representing is not really straightforward. So one thing is that I tell you there are some lots of the study in the statistical shape data analysis, and then so what they find in the shape is a kind of quantity that's the invariant to the certain transformation, such as the rotation and translation and scalings. For say in the if you see the figure in the slides, and there are bunch of the figures, they have the same shapes, but depending on the different scaling and orientations, and then the translations, they have so many different configurations, right? So then so basically the quantity of the shape is not just the coordinate of the boundaries described by those are each different configurations, and you also need to consider certain invariance and then on that the configurations. So then basically how you define the shape is you have certain configuration, but you extract some properties from that configuration, which is the invariant from the certain transformations. Then all the analysis of the shapes is also defined invariant to those are transformations. So then is the shape analysis in that sense is pretty complicated and then different from just the simple numerical analysis. So now I give the examples and then so how people are representing the shapes. And with some traditional examples, which is called the landmark-based approaches by the pioneers of the statistical shape analysis in the candles. So he defined the candle shape space and to represent some space of the shapes. And he followed some step-by-steps. The first he is interested in the some shapes of the objects, which means that's the outline of the objects. And then what is the shape feature of that outlines. So in order to represent, he placed some bunch of the landmarks over the outlines, as you see in the figures. So in the first figure in the left, you see some polygonal shapes of the objects, right? And you can put some landmark on the vertices. And then if you are getting some coordinate of each vertices, and then you can forming some configuration matrix X, that's just the collection of all the coordinates. And then in the other right figures, you see the humans, right? So postures. And then that is also based on some coordinates on the human bodies, each joint of the human body, and you can put the landmarks and then get some coordinate out of that, and then you can forming the same X matrix. That's the coordinate of all the landmark points, right? But this landmark points is a good representation of the boundary and the outlines. But this one is also containing some unnecessary informations, which is affected by the location of the objects, right? And also scaling of the objects, and then orientation of the objects, right? So then basically what Kendall did they just removed those are unnecessary factors from these coordinate informations. And the first he centered the matrix of the configuration matrix X. And by removing some translation information, location information of the objects. So just to do some matrix centering, and you can remove and all the location informations by having all the center of the coordinate to the origin. Okay. So then after that, he normalized that centered matrix normalized by the norm of the matrix. Okay. So by just removing some scaling factors, right? So that is the so-called pre-shapes. But this pre-shape is actually in the space of the hyperspheres, because that is the norm 1 vectors. So then you can easily imagine 1 point on the hyperspheres in the n-dimensional space, right? That is representing the 1 pre-shapes, right? But in this pre-shape still is affected by the orientations, right? So different orientation you have a different pre-shapes, right? So then if you are changing the pre-shape by applying the different orientations, you have some orbit over the hyperspheres. So then actually the shape is kind of defined as the equivalent class of these all the pre-shapes, which having the same shapes but with different orientations. Okay. So then so that entire 1 orbit is representing the 1 shape. That's the representation of the shapes. Okay. So then your shape space is just the collection of the bunch of the orbits on the hyperspheres. That's your shape space. So then it's the pretty complicated quantities you can imagine. So then it's now so that's the candles, but in the candles work have some major issue, and because that is based on the landmark points, and then pretty limited, and because sometimes you cannot easily identify the landmark points on the boundary of the objects, then the people later on modernize that approach with a more parametric curve based, instead of using some coordinate of the finite number of landmark points on the boundaries. People are trying to use the entire boundary as a representation of the shapes. And they do the same thing, and then they normalize out the location factors and the scaling factors and forming the pre-shapes. And then after that, they are forming some equivalent class of the pre-shapes under the rotation operators. So that is the belong to the, again, in the hyperspheres. And one orbit of the hypersphere is going to be, so you're representing the one shapes, okay? But in this case, so parametric curve is the infinite dimensional, like quantities, right? Then your space is going to be infinite dimensional hyperspheres instead of finite dimensional hypersphere. That's the only difference. But in the nonetheless, anyway, the space of the shapes are pretty complicated. So then what you can see here in the shapes are not really the very easy quantity to deal with. So they are belong to the very complicated spaces in the very curved spaces. And then, so they are the saying in they are belong to the non-vector space, and they are belong to the, is more like a Riemannian manifold space in the, specifically in the hyperspheres. But so one shape is not just the one point on the hyperspheres. That is the, like a one orbit of the hyperspheres. It's a very complicated quantities. So in these like a non-Euclidean quantities, is the making some shape analysis very hard. So because if you have a vector quantities, you can easily take some statistics by the sample means, right? And then sample covariance in the vector space. But those are in the complex quantity on the curved space, you cannot simply averaging and take a covariance very easily. Okay. So then what kind of the algebra we can utilize to summarizing observation on this complicated curved space that is going to be the major issue regarding the shape analysis. So further complication is that we now have some sequence of these complicated quantities, right? So then your entire space of the shapes are curved space. So then your sequence of the shape is going to be trajectory on that curved space, right? So then how we representing the shape sequence, that is going to be the challenging problems. And then, so usually what people do in the literatures, in the two possible approaches, so one approach is the intrinsic approaches. So that is basically they are modeling curves on the curved space directly, okay? So that is the intrinsic approaches. But as you see, this one is very complicated. And how you model is that people are using some differential equations on the curved space. And then, so because of you have some uncertainty in the curves, because you have a lot of observation of the curves, there are some uncertainties. And then so there are certain variations, right? Then instead of doing some differential equation on the curves, you do some stochastic differential equations. But the major issue is that once you have the modeling of the stochastic differential equation, you need to solve to getting some trajectory out from the differential equations. But the solving that is really infeasible practically, because if you imagine, so differential equation solving in the low dimensional space is doable, right? So, but in solving the differential equation in the very high dimensional space, like in the shape space, is really very hard computationally, because you generate so many number of the meshes to representing your differential equations. So even the stochastic differential equation is solving it in the curved space in the very high dimension is almost impossible of doing that. Okay. So then this approach is theoretically that you can do, and then so there are lots of the math paper is doing this stochastic differential equations modeling, but practically is hard to use in the actual applications. So then another approach in representing the path of the long sequence is you can do a little simpler. Okay, you have a curved space, then you approximating the curved space by unwrapping the curved space to the flat space. So then now you have a vector space of you representing all the sequence projecting on the vector space. So that is the so-called the flattening approaches. Okay. So this is a very simple but in the approximate. Okay. But in what you can do once you projecting all the sequence onto the vector space, you can use the traditional vector technique to representing the sequence on the vector space. For example, in the ALMA models you can do, and then some other time series model you can do. Okay. So then this is the more practical, but there are certain errors of the approximation because you are approximating the curve space to the flat spaces. Okay. But anyway, and this is the still in the another popular ideas. Okay. So then in this talk, and then so I'm kind of introducing each one of the ideas, and then so do some comparison later on. So in addition to that complexity, there are some another complexity you need to deal with in the modeling the shape sequences. So that is the kind of the common issue with all the time series data. So that is about the temporal variation of the time series data. Okay. So here's what I mean by the temporal variation is so you know in the time series, and you have each time point you have some quantities, right? So then the fixed time points you have a certain variations across all the observation, right? And then so you have a multiple time series data. You fix the time points, and you have some variations for that fixed time points. So that's the spatial variation. So that's about the variation in the data patterns within some fixed time windows. But also you have the variation in the time series data is even though you have exactly same data pattern change you see, and then speed of changing is the varying for the different data set. Okay, so then this kind of the variation is the so-called temporal variation of the time sequence, and then you see this kind of thing is a lot in the time series data. So then when you analyze those time series data, and certainly you need to separate out this temporal variation from the data, and then try to better understand actual intrinsic variation of the data in terms of the spatial variation and the spatial structures. So here's I have bring the very simple time series data and why the temporal variation need to be taken out before the analysis. And in the left side, you do some temporally aligned data. So that's the functional data you see. X is you can consider is the time, and Y is going to be response of the functions. So when you try to learn the spatial structure of this function, actually if data is aligned, there is no temporal variations, you can simply just averaging each curves, and then take a mean of the curves that representing the data structure very well, right? But once your data is not temporally aligned, so their jumpings are happening in the different time points, that's on the right side, right? So for that cases, if you just simply averaging the curves, you have a very weird sample means. So that doesn't represent your structure of the data. And then, so temporal variation is causing a lot of the noise on your data set, okay? So then when you try to learn about the time series data, always you need to think about how you separate out this temporal variation out of the spatial variations, need to be separately analyzed. And then later on you can combine together, but at the beginning in order to understand the data structures, you need to separate two variation sources out. Okay? So that is actually another challenges. So then in this talk, actually, I spend a lot of time for the introduction, but basically, so what I'm trying to do I used some actual examples from the human performance analysis, and to try to just explaining, so what is our approaches to handle these two type of the challenges. So I first working on the spatial temporal variations in the shape sequence issues with the motion and time study in the operation research. So because temporal variation, spatial variation have some practical meaning in that operation research studies. So then I'm using motion and time study as examples to just explaining what's the impact of the separating out to the temporal and spatial variation in the human body shape sequences. And then after that, I'm moving to the modeling itself of the long sequence of the shapes, how we modeling over the non-Euclidean spaces. And that one is I'll use some example of the statistical emulators for the human motions for the digital twins. And then as examples to illustrate what's the implications and how we address the challenges. So first is the working on the motion and time studies. and how that the temporal variation and the spatial variation, separation of them is the important. So basically, I first introduced what is the motion and time study, because these days in the undergraduate curriculum of the operation research does not really teaching this topic, right? And so then probably I'll just elaborate what is the time study and what is the motion studies. So this is a very old topic in the operation research. It's about analyzing some labor works of the humans. So just to try to use that analysis result that try to just improve the labor works. And one is like a time study by the Frederick Taylor's. So what he does he observes and then work of the humans. And then so based on the observations, and then so they divide that observation into some small work elements, and then so they are actually timing the work elements by some stopwatching and then some other like timing devices. And then just the timing is how much time each worker is the spend on each worker elements. So then after that, they are comparing that the times with the standardized time is predefined before. So that is the standard performance of the work. That is about the standard time for the completion of each worker elements. Then then is the actual measurement of the work from each worker is the compare with the standard times. Then just try to see what is that worker's work speed and the pace relative to the standard performance, and then that's the time studies. Okay. So based on that is you can see is each workers and the performance compared to the standard, right? And then based on that, and you can try to improve and also find some best practice out of this, and based on the time measurements. So another thing is like motion studies, and then so motion study by some Gilbreth families, and they are focused on some actual motions of the actual workers. And so what they do in each of the worker elements, they focus on the work motions of each workers, and then look at the variation of the work motions. Okay, so that's the motion studies. And then so purpose of this doing the practice is like they just by analyzing the work motions, they try to create a standardized best practice based on the observation and the analysis. So that's actually the motion studies. So then what I'm trying to do so this kind of practice has been done for improving the labor work in the many different locations, but this one is done by very manually, and then so by stopwatching and then so videotapings, and that's really time consuming, and over the time is hard to practice regularly for the many different locations in the many different places. So then now I'm trying to revisit these problems with some automatic motion capture data, and then how we automate this time-consuming the motion and time study with the motion data, and based on some analysis of the shape sequences. So then consider we actually measuring the work performance I. So that's each performance. Okay, I is equal to n from one from the n, so then you have the n performance, right? So each performance each time you have some human posture is the measures, right? So that is represented as the sequence of the shapes, which is the alpha IT. So then alpha IT means so human posture observations at the time t for the work performance I. So that is belong to the certain shape space, because the human posture is the shape of the human bodies, right? So you have this shape observation of the human bodies and every time moments, and then so you have a sequence of the human body shapes, and then you are measuring this repeatedly over the multiple different performance of the human workers, right? So that's the work measurements, right? So that can be done automatically with the motion motion sensors and the motion data collections these days. And then now we are imagining so that the motion data can be segmented, and then each segment is the label with the work element. Okay, so then, for example, in the entire motion is representing the one work, and that segment into the 3 pieces, and each piece is defined as the different work element. That is just the small sub operations within the work, right? So then after that, in the time studies, what you do in the every work elements, so you measuring the completion time, right? So then the T1, T2, T3 is the measures, right? So in these cases, and then so what you do so you can capture the motion variations for each work segments. So that is the kind of define the special variation of the postures for each work segments, right? So that kind of in the special variations. So these special variations capture for each of the work elements, right? So then another thing is that you also capture some variation in the T1, T2, and T3. That is about the temporal variation of the sequence, right? So then it's basically when you do this practice with the motion data, actually if you are analyzing the temporal variation, that's the completion time of each work elements, right? So in relative to the standard performance, is going to be the time analysis, right? So then the analysis of the temporal variation is going to be time analysis in the traditional motion and time studies. And then analysis of the special variation, that is the variation analysis within each work elements, right? So that the analysis of the special variation is going to be the motion studies, right? So then once you have each of the studies of the variations and the different variation source, you can do some correlation analysis between the spatial and temporal factors, and then that is going to give some the motion and time studies. So then basically this one is how I perceive and how we use the motion data can be used for the motion and time studies. So then how we perform this type of the studies and how we build some mathematical foundations to performing this. So that is going to be in the upcoming slides. So then basically the formulation for the time analysis first, and relative to the standard performance. So basically we are looking at the variation of the completion time of each work segments relative to the reference, right? So then we first set up the reference, so which is defining the standard performance. So suppose there is a reference motions, okay, that is following the actual standard operating manuals usually available in the industries, right? And that they performing some standard manuals, and then that defining some sequence of the motion, which is the reference motion, alpha R. So then they are usually already task segmented and then labels, right? So then you have each time points of the reference motions, you know what is going to be the segments of that alpha. So once you have the reference motions, and then now you start actually getting some observation of the worker performance. So then the ICE work performance is the alpha I. So that is the kind of sequence is the mapping from the actual time frame of the performance 0 to TI, right? So then each performance you have a different time length, and then because of the different efficiency, then your sequence of the shapes is going to have the different time frames, right? So then that's the 0 to TI. Each time point in that time frames, and you have some posture of the human workers that is defining your work performance, and that sequence is representing the actual work performance by the workers. Okay. So now we like to compare. So how work performance I has the executed, and which relative to the reference motions. So that is done by actually like a time alignments between the reference motions to the actual motion alpha I. So suppose you have a reference motion alpha R, right? So then you have a bunch of the standard postures over there. So you have below, and you have alpha I, that's the actual observation of the work performance I, right? So then is the now you like to mapping in the which part of the alpha I is corresponding to the reference motions, right? So that is the expressed as the some time alignment function between the alpha I to the alpha R. So then the which point of the alpha R is correspond to the which point of the alpha I, right? So that mapping is expressed as some non-decreasing function of the between the two different time domains. So then each time points of the reference points, and then how that is correspond to the like a time point on the actual performance of the worker I. Okay, so then so that time mapping is represented by the here the gamma I, right here, and then that's the mapping between so two different time domain, how you map to each others. So that defining actually the mapping between the reference and the actual observations. Okay. So then is the once you have that the time alignments, and then how you get this is the I'll explain later. But once you get that, and then that the time alignment function implying the quite implications. Okay. For example, in the gamma I t is the equal to V means, and the work performance I at the time V is correspond to the standard performance at the time t. So this one is the giving us some information about how the work performance is the paced with a different speed compared to the standard work performance. So then how we get that the gamma I is going to be crucial because that's about the time variation, temporal variation of the sequences. Then is so we formulate some optimal temporal alignment problems and aligning so observed sequence to the reference sequence in terms of the temporal aspects. And then the gamma I is going to be alignment functions, and we try to minimize certain distance between aligned sequence to the reference sequence. And then that is basically minimizing the sequence to sequence distance. So when you calculate the distance between the two sequences, and you are using some difference between the two different postures for the aligned sequence, and then so reference sequence. And then for that we are using the shape matrix because this is each posture belongs to the shape space instead of using the Euclidean matrix, and we are using the shape matrix when we compare the aligned sequence to the reference sequence. Then by minimizing this metric, and we can find and which alignments giving the best alignment to the observed sequence to the reference sequence. So then once you solve that optimization usually you can do some dynamic programming to optimize that optimization. But once you got the solution is you can now analyze the variation of these alignment functions, because that time alignment function is providing some large of the useful information. So that alignment function is basically shows some work progression of the ICE performance. So that can be interpreted by looking at actually what's the meaning of the value of that gamma functions. Okay, so if the alignment function of the work performance I is equal to V at the time t means, so like what I said before, work performance in the I at the time V correspond to the standard performance at the time t, which means the work performance I is complete the t portion of the standard performance by the time V. Okay, so then the value of this gamma function is basically defining the work progressions of the work performance I. Okay, and then by plotting this gamma function over the multiple performance, you can look at the variation of the time performance of the different work performance. Okay, so this is the one a plot that we did with actual data from the factories, and we have 60 sequences, and we aligned each 60 sequences to one of the reference motions, and we plot that alignment functions, and then we have 60 curves over there. Okay. So one of the observations that we see is the alignment function for the reference motion is that's aligning the reference motion to itself, right? So then that alignment function is going to be identity map, right? So which means your reference motion standard performance having some alignment function is just a linear line, right? That's the identity map, right? So then you can now see your gamma function relative to the standard performance is how they are differ to each other. So that giving you actually the which performance is the surfacing the speed of the relatively in the reference motions or not. Okay, so that is the kind of the implications of the temporal alignment functions. So then we are utilizing that in the basically is how people are performing relative to the standard motions. So then further we can take a derivative of that alignment function that representing the instant speed of the work performance I at the time t. So because alignment function itself in the cumulative progression of the work. So now we take a derivative that's the instant speed of the work at the time t. So then what we do so we take a time derivative of the gamma functions as the speed of the work at the time t, and we take the logarithm with some regions, but that has the very nice properties. The one is we looking at the baseline, that's the speed of the standard performance. So time derivative of the time alignment function for the standard performance is going to be the constant. So because gamma r is going to be identity map, derivative is going to be just 1. So that has the constant speed. So that's the baseline. So if you take the logarithm of that, and then that logarithm is going to be zero-valued function, that is going to be a speed for the standard performance that is forming some zero baseline. So now we are getting that logarithm of the actual performance of the I, and then getting so Ri of t, that's the logarithm of the derivative of the alignment function for the work performance I. So if that work performance I has the Ri is the positive, that means instant work speed of the work performance I is the faster than the reference motion at the time t. So if the Ri is the negatives and the instant work speed of the alpha is the slower than the reference motions at the time t, then we can just plot by plotting this derivative logarithms, and then you can look at how other people are working on, and then what's the variation of that. That is basically in the time analysis. Okay. So then in this figure we plotting the 60 sequences again from the factories, getting some time alignment functions, take a derivative of the first derivatives, and then take the logarithm, and we plotting, and then so we compare with the zero baseline that corresponding to the standard performance. Okay, so then each portion of the time x, and you see is sometimes average performance of the people from the 60 persons and go below, and then zero baselines, which means so normal speed of the people having slower progressions compared to the standard performance. So then the most of times, and then you can look at it, and then so basically from there you are attempting to adjust your standard operating manuals, and by changing the standard work times. So that can be done based on the analysis. And another thing is what you can see is what's the variation between the workers and the worker performance and over the times, right? And so across the different performance, and then so what is going to be the variation depending on the different persons by looking at the variation of this log first derivative of the time alignment functions. So that's pretty much forming the time analysis. So then once you have all the time alignments, and then so you can standardize all the observation by do some temporal alignments. So basically you can take alpha I and then composition with the temporal alignment function. You can standardize all the data to the temporally aligned. So once you have the temporal alignments, what you can do in each time points, and you can do some analysis of how the postures of the different performance are changing, right? Because all the data is the temporally aligned and each time points, and then you capture some the posture data, right? And then you look at what's the variations over the postures, and that giving us what's the variation in the work motions per each time of your performance, right? So that's the basically in the motion analysis what you can do. Then is how you describe the variation in the shape space is going to be the questions. Okay. So let us first do in the very simple statistical analysis, which is the taking the mean, right, of the observations. So then you have sample data, right, and each time moments, and you have some posture observation which is aligned temporally. Then is so that observation is already representing all the motions, and then for the same work segments because they are aligned in the temporally, right? So then this capital DT is like a collection of the observation of the posture for the work segments at the time t in all the temporary line, right? So then we try to take a chain mean of that sample is by taking some intrinsic mean of that posture shapes in the sample data. Okay. So the user is when you take a sample mean is you can just take a summation and then averaging out, but that is the vector technique, right? And you cannot do so all the data is belong to the manifold space. So in the manifold space, you just generalize the concept of the sample mean as the mean is some quantity minimizing the square distance between all the sample points on the space, right? So then we have some intrinsic shape mean over the shape space, and we are using that same metrics to define the square distance between the mean and the sample points, right? Then we are minimizing that the square distance over the summation of all the sample distances, right? So then finding the sample points that minimizing that the summation of all the square distances, that is going to be the centroid of the sample points you get from the DT, right? That's going to be the center of the distributions we can define. So once we have that the center, and then what we can do when we define the variation is we basically creating some tangent space that is tangential space in the center at the sample mean. Okay, so then that's the centroid of all the observations in the DT. So we are getting actually the tangent space around that means, which means you are projecting all observations to the tangent space around that the sample means. Okay, then you have some Euclidean vectors that belong to the tangent space, right? So in that the vector space, you can calculate the sample mean of that Euclidean vectors on the tangent space that is going to be define the variation of the data. Okay, so basically this is approximate mean, but the people are using this for the defining the variations, and then there are not much else is that you can do, and more than this. Okay, so basically you projecting data points on the tangent space, taking the sample variations. That's the so-called the cultural mean that representing the variation of the data. So then is each time point you get the centroid and you get the variance, and that describing variation of the motions, right, around the centers. So then you can do the PCA over that tangent vectors, right? And that is the so-called shape PCA. You can do the PCA analysis with that sample covariance. You can identify the principal direction of the motion variations. And here's in the first one is going to be variations of the first principal component direction. This one is the second, this one is the third. So then you can just analyze what's the variation of the shapes over the PC space. So even more, and so what you can do you can do some supervised shape PCA, which means, so basically what you can do is you like to know what is the direction of the posture variations highly correlate to the work rate. Okay, so then it's not just you are looking at the variation of the posture variation, but you interest in the direction of the variation correlate to the work rate. So that is the basically in the supervised shape PCA is doing. And basically what you do you do PCA on the conditional covariance of the conditional expectation of the postures condition on the work rate. So that is the basically ideas. And then is the you can kind of in the projecting in the with the for the high rate of the work speed, what is going to be the motion is going to be like. And then for the medium rate of the work rate in the what is going to be the motion is looks like. So then based on that is that you can kind of define some best practice out of the motion variations. What is going to be like motion variations, so that explaining the best practice that providing some fast work speed. So that's the pretty much in the what you can do with this supervised shape PCA. Okay. So then this is the completing some actual the motion and time study. And basically in the summarizing, so we do some time analysis is defined by the temporal alignment of the sequences to the standard performance sequence, right? And then so we analyze the temporal alignment functions by looking at the variation of the temporal variations. And then through that you can kind of look at what is the speed of the work and the relative to the standard performance. And then through that you can define what is the normal speed of the peoples and in the facilities. Then you can redefine your standard performance and the standard speed. And the motion study is the ones you have all the alignments and each time points align and you do some analysis of the variations. Through that you can identify what's the effective motions that providing the best faster work rate. And then that is the motion and time studies in the completed. Okay. So I think the time is almost 12:52, and then probably I skipped this part. The basically I'm quickly summarizing. So beyond that simple mean and covariance analysis, and we try to build some statistical model over it, and then so getting some joint distribution of the human motions over the long sequences, and then using it for emulating actually human motions for actual simulation of the human performance, and for the using it in the emulating and simulating actual work in the simulation model. And that is we are actually the visioning, but given the time limitation, maybe I skip this and then just jumping to the very last slides. So just a simple takeaway, and then we discussed the two important research, but I pretty much discussed only first one. And we do using some shape analysis and then modeling the shape sequence to just apply for the motion and time studies. And then here's basically is the important steps you need to take away is when you analyze the long sequence. So separation of the temporal and spatial variation is provide the useful analysis of each one of them. And the later one is after separation, you can correlation study between the two factors that provide another important studies. Second one is we have something statistical model for jointly modeling of the motion and the temporal variations, and then so that providing some simulation capabilities in the actual human performance. And then that is pretty much in my talk, and thank you for listening. Yeah.
Let's thank Dr. Park for the wonderful talk. Any questions?
Can you go to slides 22?
Okay.
So y is the maximum value of y-axis is 1. You did a scaling of the observed sequence?
Yeah, actually, that's the good observation. And then so we scale the time scale of each observation by normalizing that by the total times. And then, anyway, and then so that total time is the only explaining the total time of the performance to the ends, right? And then so right now we are looking at the actual relative performance compared to the standard operations. Then we just normalize out the TI and then look at actually that range.
Okay. So in your data set, so what is the sampling frequency of the shape sequence? For example, typically how many samples you have for one series?
So normally we have more than tens of thousands and the points, and then every seconds we have 10 points observations. Yeah.
Okay.
So but certainly we can downsample to the certain points because every 0.1 seconds really the posture really didn't change much, right? Yeah.
Okay, yeah, in that case, do you have a scalability issue in the optimization? Because to get this gamma function, you need to optimize, right? To find
but in good thing here is the dimension to optimize is just one dimension in the temporal dimension, right? And then another thing is that the function is the non-decreasing functions, right? And then so that is the limit the large of the solution space. Then is this is a very doable. But certainly if you have so many sequences and then it takes time, but each sequence is you optimize individually, right? Then number of observations is just affecting the linearly, and then so same thing for the optimization for the each optimizations in the complexity is increasing in the linearly in the number of time points.
Okay, thank you.
Okay, another question?
Yeah, a great talk. I just have some questions related to other alternative approach to tackle this problem. So regarding learning this function gamma here the formulation looks like a dynamic warping, right? So what is the difference here? Because dynamic warping also try to learn the scale of the two signal, right? By somehow using similar kind of setup. So what is the difference?
Yeah, basically this one is so it's usually when you do some a time series and you have some time warping, right? And then so aligning the data, right?
Right.
So major difference is usually in the time warping and you do using some Euclidean metrics, right? And because the data is the numerical data, right?
Right.
So but then here's one difference is we are using some shape metrics, okay? So then if you are using changing the metric to the shape metric in the non-Euclidean space, and then so conventional time warping algorithms, so defined with the Euclidean metric cannot be applied for this. So then with the change of the metric and your time warping algorithm is going to be changing with the different metrics. Then what we actually, I haven't explained the details, but basically we have some a specific representation of the shapes for these cases that is optimally work for this time warping with the different non-Euclidean metrics. So that is the kind of contributions in the roughly, yeah.
I see.
Yeah.
So in other words, somehow you can view the dynamic warping as a special case,
right.
For this type of
exactly, and then so Euclidean is actually basically in the very nice properties, and then for example if you are putting some different warping functions, and then so the Euclidean metric with the time warping functions invariant to with the different choice of the warping function, so that is utilized for optimizing this a warping objective function very easily. But if you are replaced with that Euclidean metric with the shape metrics, and then that property doesn't work at all. So then the people are thinking in the different representation of the alpha, and then so with that same property shared with the Euclidean metrics. So that is the kind of something new here, and then so we develop some new representation and the modification of the alpha I, and then time warping is the more efficiently solved.
Okay. So can I ask a second question?
Sure.
Because this is very intriguing. So so regarding this poster modeling, you can regard this as a multivariate profile data, right? Functional data.
Right.
So I remember I see some other work when they deal with the multivariate profile data, they try to use a sparse sparse decomposition kind of approach, modeled like a mean profile and then some variation.
Right.
So all using a even functional PCA, right? So what is the unique benefits of go through these routes? comparing with other type of those decomposition type of sparse modeling approach.
So I think it's actually eventually we are following the routes of the sparse decomposition. But in the how you do that, the sparse decomposition is usually defined on the vector space, right? And then, but you cannot do the vector space here. Then, so eventually I missed the very important part of the presentation is how we, so doing some vector representation of the approximation of
I see.
Yeah, that is the kind of something new. After that is actually we do some sparse PCA and the functional PCA to, yeah, but in the how we go there is going to be something new. Yeah.
Okay.
Yeah.
That's all my question.
Okay.
Yeah. Okay. So now time is up. So let's thank the speaker again for the wonderful talk. Yeah. And yeah, and this is the end of this colloquium. Thank you very much for attending.